So we are going to see today about analog to digital converter interfacing and stepper motor interfacing to 8086. So in the last class we have seen how D2A converter is interfaced to 8086, and to demonstrate that we have seen like generation of few waveforms like square wave, triangular wave and rectangular. We will try to see how to interface analog to digital converter to 8086 and how to interface stepper motor to 8086. So this is what we try to see in today's class. Okay. So now let us start with stepper motor interfacing. Anything is all right, analog to digital converter interfacing or stepper motor interfacing. So now let us try to see stepper motor interfacing and then analog to digital converter is what we can go ahead. These experiments you try to do in your lab. So parallelly, I'm a little bit slow here because you have to do the same thing in your experiment in the lab, related lab. So now let us go ahead. Let us try to see the stepper motor interfacing, how it can be done and all. So first what we do is we will try to see the hardware configuration, like what is exactly the stepper motor, how it looks like, and if you want to rotate the, so why coming to the motor, a motor, we have different types of motors like stepper motor, DC motor and AC motor. But stepper motor is a special type of electrical motor that moves in incremental or steps rather than smoothly moving in either forward or backward directions. So coming to the applications, now if you try to see the applications here, okay, so now this is an industrial application where you are using this robot is placing this object. So placing these objects on a holding device accurately so that the produced items will go out. So that kind of applications. So the robot arm has to move accurately to the specified angle from here to here and carefully place the objects here. Okay, so in these kind of applications, right, so the robot is picking the object and then it is trying to move on this particular holding device which is moving on a belt. So the holding device is moving like this. So the movement of the robotic arm should be precise. So these kinds of applications we can use stepper motors. Right. So now you can see here how it has to put. And then here the stepper motor can be used to read and write. It is used in read and write of your printers, okay, or hard disk. Okay, something you want to write into hard disk or something you want to read from hard disk. So the movement of the reader on particular when disk is rotating, you can use stepper motor. And this is one more applications where stepper motor is widely used. So this is the paper feeder. It is a paper feeder on printer. So when printer is moving, the stepper motor, is moving the paper accurately so that the letters will be typed on a sequence. So if you try to see dot matrix printer, so dot matrix printer, so in dot matrix printer, here you have two stepper motors. One is to move the paper to a required position, and another motor is used to move for printing the characters rightly on the paper. So this is one more application of the stepper motor. And another application is CNC lathe machining. Okay, proper cutting of your metal. Stepper motors are used. So now coming to the advantages of why the stepper motors we are going to use. It is a low cost for control, low cost devices, easily controlled, and low maintenance, and it will work in any environment. But it requires a dedicated control circuit, and it uses more current than DC motor. But precise positioning systems will be using stepper motor. And these are the other applications of stepper motor in industry. High speed pick and place equipment, multi-axis CNC machine is what we have seen, directly driving lead screws and ball screws. And in optical applications you have linear actuators, linear stages, rotation stages, goniometers and mirror mounts. In commercial application you have floppy disk drive and computer printers, image scanners and compact disk. And it can be used digitally controlled and more rugged, so that they are used in packaging machinery. So packaging machinery also it is going to be used. So many applications have stepper motor. So now how the microprocessor controls the movement of movement of a particular device using stepper motor is what we are going to see in this particular class. So now the objective is, here this is what your 8086 microprocessor. Here this is what your 8086 microprocessor, and stepper motor. Okay, stepper motor is used for precise positioning here. So we need a positioning system like robot where we have seen. So a precise positioning is what we need. Precise positioning is what we need. So here we have stepper motor to do that. Now 8086 has to control the movement of the stepper motor. But as the 8086 has the pins, it can send the data through its data bus D0 to D7. But when it has to, when it is giving the control bits like ones and zeros to the stepper motor, if they are connected to the windings of the stepper motor, then the pins will get damaged. So what we need here is to excite the windings of the stepper motor. We need to boost up the power. So we need power amplifiers and isolation circuits. Okay, isolation circuit. Right. So these power amplifiers will supply the required power. If the stepper motor is having 4 windings, so then that will try to give it through power amplifier. But if the stepper motor is drawing more current, then the pins of 8086 will get damaged. So what we do is, we will try to interface that through 8255. It's a programmable peripheral interface. Right. So the data which we are going to, the command bits which we are going to give it to the power amplifier, we are going to give it through ports, and here the port, okay, will carry the command because the processor is working with 5 to 10 megahertz. So within microsecond it can give data. So then that particular command, if you excite, this has to be holded for a delay. The windings of the stepper motor has to be excited for certain time. So it has to be holded. So then we will configure our programmable peripheral into output port. So it holds the data, and the current supplied by these port pins is not sufficient to excite the windings of the stepper motor. So then here we will be using power amplifiers. So here we will be using power amplifiers, and the power amplifier output is connected to the stepper motor, and stepper motor will be connected to the required positioning system. So this is what we try to do, and this is what we call stepper motor interfacing circuitry. Yes, sir, stepper motor interfacing. So now let us try to see. Now, to control the movement of the stepper motor, we have to see the constructional details of the stepper motor first, and then how we are amplifying the current, the driver circuit for the motor, and then how you are programming your 8255 to configure the port punch, and how you are writing a program to interface the stepper motor to moving it in forward and backward direction. Right? So now let us see the constructional details. Now, if you try to see the stepper motor, this is how it looks like. This is of stator coils, and this is of rotor. Right, and more in detail if you try to see, this is a simple electromagnet. When you supply the power, if this is your positive terminal and this is what your negative terminal, so then the current will be moving. So north and south poles will be formed. Right. North and south poles will be formed, and the electromagnet we can create. So here we have two windings, rotor winding and stator winding. And here if you try to see the cross-sectional details of the stepper motor, it looks like this. There is the internal components. So here you have the stator and stator winding. Right, it is stator and stator winding. It is a four-phase motor, right? And then the rotor has teeth, as we seen in the figure. The rotor has teeth here. Here, if you try to see, the rotor has teeth. Right, so the rotor has teeth, and now if you try to see the working of it, the top electromagnet here is turned on. If it is turned on, then this will be attracting the nearest teeth. This will be attracting the nearest teeth of gear-shaped iron rotor. So with the teeth aligned to electromagnet 1, they will be slightly offset from electromagnet 2. So then if the top electromagnet, if it is turned off, and then the right electromagnet is energized, and then the pulling of the nearest teeth is slightly to the right. So this results in a rotation of a required angle. That is based on the number of rotor teeth and stator teeth. Right. So if it is energized like and third electromagnet and fourth electromagnet, and then it can complete a rotation. So the stepper motor will be continuously rotating. If you excite the electromagnet 1 and then 2 and then 3 and then 3 and then 4, then that will be rotating the rotor. This is a simple motor working principle, is what you can see. Now, the constructional details of an electromagnet stepper motor, if you try to see, so then the stepper motor, yeah, this is what the widely used stepper motor, 4-phased. So then here you have positive and positive stator windings and negative and negative. Right, electromagnets. Right, and then now if you try to see the permanent magnet with 6 phase. Right, now if you try to see 1, 2, 3, 4, 5, 6, 7, 8 phase, then you can see like you will be precisely controlling, powering up. Rotating the rotor will be very accurate. So now coming to the rotor will look like this. And so this is what the rotor, which is having the number of teeth. And now if you try to see the motors, coming to the motors, there are 3 types. One is permanent magnet stepper motor. Another one is variable reluctance stepper motor. Right, variable reluctance stepper motor. And then the third one is hybrid motor. So now widely used one is the hybrid motor. So now this is what we use widely. So it looks like this. And the internal details of this, if you try to see, it will be having stator windings and then the rotor teeth. And more in detail, if you try to see, the rotor is made up of soft iron and 2 couplings are connected to an electromagnet, and when these 2 are joined, right, 2 are joined and will be forming North Pole and South Pole. So this is about the rotor, is what we are discussing of hybrid stepper motor. Right, and this rotor, when it is moving, one cup will be rotating, giving precise angle. And the 2-dimensional cross section of stepper motor, now if you try to see, then here you have the stator teeth and then the rotor teeth. So these are the rotor teeth. So the widely available, the commercially available stepper motor has either 200 rotor teeth or 400 rotor teeth. And the angle of the rotation, X, can be calculated as 360 degrees by the number of rotor teeth and stator teeth, if stator teeth it is having. So now all together, if you have the rotor teeth 400, rotor and stator teeth 400, so then the incremental step is 0.9 degrees. 0.9 degrees is what you can control. And typically available has 200 rotor teeth, rotor and stator teeth. So then 1.8 degrees is what the minimum step angle you can go for. So if a rotor is having 200 teeth, then that will be, X will be coming around 1.8 degrees. Right, so now coming to the stepper motor specifications, the typical stepper motor may have a torque of 3 kg centimeter and operating voltage of 12 volts. This is what important you have to see. To operate this motor, you need 12 volts. Different motor specifications are available. This is one motor specification. And current rating is of 0.2 amperes. And step angle is of 1.8 degrees. This is how they mention. Means what? The rotor teeth is of 200. And to excite the field windings, you need 0.2 amperes current. And the voltage you need to apply is of 12 volts. Then, now the speed of the motor is determined by the time delay between each increment movement. And the stepper motor can function in 3 modes. One is full step mode, half step mode, and micro stepping. And now let us try to see the hybrid motor is what we are talking about. And now if you see the full step mode, in full step mode you will be supplying, means all the field windings will be excited, and like here like 1010 kind of thing, and then you will be getting full torque. And this is what full step, that means 2 windings at a time they are excited. 2 windings means the maximum. And in micro stepping, what we do is, this is what generally these days used for precise positioning control. Here we try to supply a signal of this kind so that precise movement of stepper motor is possible. So micro stepping is the mode generally we use for in industrial application. And now if you try to see the torque curve, right, so which motor has to be preferred, that depends upon the torque requirement. So as the frequency increases, so then the torque increases. So this is what your slew range, right? So the pull out torque and then pull in torque, and then the maximum frequency which you need to supply. And this is how, recalling, one phase, this is a full step. So when it is full step, one winding is excited, 90 degrees is possible. And then this is 2 phase on, full step means 2 windings are switched on at a time, are supplied power at a time, then 45 degrees is what it is possible. So now the same thing is depicted here of the motor. This is what the full step operation. That means what, 1 winding at a time. And in half step operation, 2 windings will be excited at one, so that you will be getting 45 degrees, right? So now each winding is represented with this coil symbol A and B. This is winding 1, this is winding 2. So 4-phase motor, stepper motor is what we are dealing here in this particular application, right? And then these are the rotor teeth. So this is a 6-pole rotor. Then one step is of 15 degrees. So now how many steps are required for one complete revolution? That you can calculate. So now let us try to see the total steps required for one complete rotation. Then one step angle of, if it is the rotor teeth, if they are 200, stator rotor teeth, they are 200. Each step angle would be 1.8 degrees. And then now for one rotation, how many steps need to be performed, you can easily calculate. So the revolutions per minute can be calculated as RPM is equal to 60 into steps per second or second how many steps by steps per revolution. Right. So now this is how you can calculate the RPM. Right. So this is what the constructional details we have seen. Right. And now coming to the motor winding, four-phase motor is what we are considering, which has four windings: WA, WB, and WC and WD. Okay. Now each coil is excited once. So coil 4 is on, then coil 3, coil 2 and coil 1 are off. Then coil 3 is on and coil 2 is on, and then coil 1 is on. Okay, coil 1 is on. Right? So these, so we have to excite the winding once at a time, 4, 3, 2 and 1. Right? So then now this will be the command we need to write into the stepper motor. 1 0 0 0. This is of 1 0 0 0. Next 0 1 0 0. And next 0 0 1 0. Each coil is excited at one time. And 0 0 0 1. Right? So then this is the second one which we talked about, 2 at a time. 2 coil excitation. This is single coil excitation. But now we are going ahead with only single coil excitation. So then we leave it. If it is 2 coil excitation, 3 modes of operation is what we discussed, right? So 1 1 0 0 is what you need to give. 0 1 1 0 and then 0 0 1 1 and 1 0 0 1 is what you need to give in 2 coil excitation. So interleaving the 2 sequences will cause the motor to off step. So 8-step sequence, then you will be having normal 4 steps plus wave drip 4 steps. Right. So this is what it is depicted here. So then this is what single coil excitation, 2 coil excitation and off stepping. Now we are going ahead with single coil excitation at a time is what we are considering for this particular motor. So now if we try to see for clockwise motion, for step 1, coil A is excited first, then coil B is excited next, coil C is excited next, coil D is what excited next. And then at 5th step again 1 0 0 0. This is for clockwise direction. And then the equivalent hex code is 8. And for anti-clockwise direction, and we need to, for step 1, if coil A is excited, then coil D is excited, then coil C is excited, then coil B is excited, and 5th step again coil A is excited. So we have seen the stepper motor and stepper motor in internal constructional details, which has 4 windings. Those 4 windings equivalent is what we are taking out, and to connect these 4 coils we need 4 port pins of 8255. And this is what the construction, this is what your 8086, and this is what your 8255, and port A is what we are using. Now let us take, this is port A0, port A1, port A2 and port A3. These are A, B, C, D, 4 coils of stepper motor, and this we are giving it to a power amplifier to excite the stepper motor coils because it requires 0.2 amperes is what we have seen the specifications for one particular motor. So this is what the interfacing you have. And the stepper motor has to be excited with 12 volts, but the power supply which you are going connecting to 8086 to 8255, and then the 8255 has the port pin. So now each pin can have logic 1 means it can be of 5 volts, 0 means it can be of 0 volts or ground potential. So we need to give 12 volts excitation for the stepper motor. So we need additional power supply. So this is what the block diagram connection. And now here we need power amplification plus the driver circuit, and the power amplifier circuit or the driver circuit. So the driver circuit can have transistor driver. In the sense, to amplify the current, we will be using Darlington pair, or you can build your own self. So now we will be using transistor drivers. Now if you try to see, let us take, this is what the stepper motor coil, and the stepper motor coil, you are now from 8255 port, you are connecting it to a stepper motor coil. So it can be connected through a freewheel diode like this, which is shown in figure. Now the current supplied by the port pin is not sufficient to excite this coil. So we are amplifying the current through transistor Q1 and Q2. If the beta of the transistor, if it is 20, and the beta of this transistor, if it is 50, so then 100 times the first base current will be amplified beta times, and this collector current will be driving the second collector current, so which will be amplified at least 1000 times. Great. And that high current will be driving your particular coil. Then we will be using a diode here to protect your transistor, because when the transistor, when it is off, when the transistor, let us take, you are not exciting this coil, then the port pin will be giving 0 here, and then if the transistor is off here, so then when this transistor is in off position, then the current, the high current which is flowing through this coil will not become 0 immediately, because the inductor opposes the change in current. So voltage will be developed here. So that voltage can break down your transistor. That voltage can break down your transistor. So to avoid that, a diode is connected here so that it can clamp the voltage across the coil to 0.7 volts. So that is the use of this freewheeling diode. So then this is, if you have your load here, so this should be a PNP, Darlington pair connection. So now here if you try to see from port B you are getting, so let us assume the load current is 200 milliamperes. 200 milliamperes, which is of 0.2 amperes, which is a required excitation. So then the maximum sourcing current of port pin, now if 8255 port pin, if it is giving only 1 milliampere current, but we want that to be 200 milliamperes. So then IC maximum should be greater than 200 milliamperes. So the IC maximum should be greater than 200 milliamperes. So the HFE minimum should be IC by IB maximum. So IC by IB maximum 200 milliamperes by 1 milliamperes, it is of 200. So the beta of the transistor which you have to use here, it is of 200. So then the power dissipation by the transistor which is of VC SAT and IC maximum. So VC SAT is of 0.2 and then IC maximum is of 20 milli. So then the transistor should be a power dissipation rating of 40 milliwatts. So then if you have these in details, then the RB, to safeguard the transistor, RB is 4.8 minus 0.8 by 1 milliamperes, which is of 3.7 kilo, assuming the output high voltage of port pin is equal to 4.5 volts, 4.8 volts, and then this, if you try to take 0.7 or 0.8, so then by 1 milliampere means here to restrict this, then you have to connect a current of a resistor of 3.67 kilo ohms, 3.7 or 4.7 based on the requirements as just now we connected. So here it is of winding A, B, C and D connected to power amplifiers. So connected to power amplifiers. So it will be connected to port A0, this will be connected to port A1, port A2 and port A3, PA3. So it is TIP120 is a Darlington transistor if the motor needs several amps. Right, this is to the stepper motor. This is what the hardware connection, and this is what you can see now. This is what your port A is connected to the Darlington pair, and now this is, the motor has four windings, like this is 1, this is 2, and then this is 3, and then this is 4. Right, so these are the 4 wires are connected, and here you will be supplying plus 12 volts. Okay, not yet. So here you will be supplying plus 12 volts to the coils, and the hardware connection is like this. This is what your 8086 microprocessor, and this is what your 8255 pin. So the D0 to D7 of the microprocessor are connected to D0 to D7 of your 8255, and PA0, PA1, PA2 and PA3 are connected to the coils as we discussed now. Right, these coils, you have 4 coils, right, and then this is what the hardware connection. This is what the hardware connection, and this 8255 may have that there will be having the equivalent address, and the decode the address by using these pins. Okay, the address things. Is it all right? And then now let us take, so this is what your complete hardware details of stepper motor with 8086. Right? So now let us write a simple program. The problem is this: design a stepper motor controller and write an assembly language program to rotate shaft of 4-phase stepper motor. Right, so you have to rotate the stepper motor in 5 rotations and anti-clockwise 5 rotations. You have to rotate the stepper motor 5 rotations in forward direction, clockwise direction, and 5 rotations in the anti-clockwise directions. It is a 4-phase stepper motor, and the details should be given. So then the command word which you have to give is 10000100, so on. For clockwise, this is the command word you have to give, and for anti-clockwise, this is what the command you have to give. So now let us try to write the program. So now to do this, let us write the algorithm. So this is what the hardware you have. 8086, so data pins are connected to 8255 and 8255 ports are connected to the power amplifier, and the power amplifier output is connected to the stepper motor windings. Power amplifier in the sense we are using Darlington pairs. So now the step number 1, initialization of 8255 as an output port, because the command words we are giving. So 8086 is a controller now, controlling the direction of stepper motor. So step number 1 is initialize. So initialize 8255 as output port. That is your first step. And the second step is you have to move the stepper motor in forward direction. So forward direction means, so the next step is move the stepper motor in forward direction. In forward direction. So then the equivalent command, which is of, so now here you have 1000 is the command you are giving, but 8086 is it can send 8 bits or 16 bits at a time. So now if you try to take 8 bits at a time, so now let us take, this is your D0, this is your D1, then this is your D2, this is D3, and this is D4 and D5 and D6 and D7. And the command for clockwise direction we need to give is this first, and then next this one, and then next this one to excite the windings, and then the next this one. So the moment it is rotated, and one more, it should be, right rotation. You have to rotate this to the right. So if you rotate it to the right, after 1, 2, 3, 4 clock pulses, it will goes to, this will goes to D7. So then it will become 10000000. That means the motor is off now. If it is connected to PA0, so now it is connected to PA0 and PA1, PA2 and PA3. Right. So then it will be off. So then we need to send, so moving the stepper motor in forward direction is done through sending a control word. Sending a control word. The control word is suitable control word. So the control word, if I try to take it as 88 instead of 08 as we taken earlier. So now if I take this as 1000 and then 1000, which is of 8 and 8, one right rotation if I do, then it will come here, and then this will come here. And then another right rotation, this will be coming here, and then this will be coming here. And another right rotation, it will be coming here, and it will be coming here. So after 4 rotations, this bit will come here, 1000, and then this bit will be shifted here, 1000, then you will be getting continuous rotations. And it will be continuing. So move the stepper motor in forward direction by sending a suitable control word. By sending a suitable control word. Then the third step, you will give a control word to the port where the stepper motor is connected, and then you have to give the delay. Why? Because the stepper motor winding has to be getting excited. So for excitation of the field winding for certain time, you need to give a delay. So then give the next command. So step number 4, right, you give the delay. Again, the next winding has to be moving in clockwise direction means the next winding has to be excited. So then set that means here what you do, rotate the control word to right and send it to port A, right? And this should be in loop until 5 clock rotations you get, right? So then step number 5, check 5 rotations, 5 full rotations are completed or not. Then if not, go to step, so here step, right, go to step 2, then if completed, so then rotate the stepper motor in anti-clockwise direction by sending suitable command word, which is of 88 in this case. Then give delay because the winding need excitation. Okay, so then delay would be around 10 millisecond delay you can give for field to be getting excited. So then here step number 9, rotate left, then step number 10, if 5 rotations are completed, check if 5 rotations are completed or not. Then this is rotate left. So this is rotate left is what the command word for continuous rotation. So you have to go for continuous rotation. Continuous rotations can be done by using rotating the command word to the left, right? And then if 5 rotations are completed, right? If not, go to step 8. Step 7 means rotate stepper motor in anti-clockwise direction by giving the command. So go to step 7. Then if they are finished, if it is completed, then stop. So this should become these algorithm steps should become as an instruction. So now let us try to see this in a code. Now as we discussed, this move AL comma 80 and out AL to the address of the control word. This 80 already we have seen. D7, D6, D5, D4, D3, D2, D1 and D0. Simple IO mode, this should be 1, mode 0 application of group A 00, and then port A is an output port 0, and port C upper, anyhow we are not using that 0, and this is what group B control, 0 means mode 0, group B is output port, we are not using anyhow, here it is 0, and port C lower it is 0, so this is what 80 command we are giving. So this is what your initialization of 8255. Initialization of 8255. Then move AL comma 88. Move AL comma 88 is the command word is what you have to take, which is of bit pattern 1000 and 100 is which we have discussed now. And you have to load a count. How many rotations you want? You want 5 rotations. So 500 into how many rotor teeth? The stepper motor is having 200 rotor teeth. So 200 into 5, then which is 1000. So the count to be loaded here is 1000 for 5 clockwise rotations. So load the count and write this command word to the port A where your stepper motor is connected. So when you are doing this in your lab, if you are using electro systems or Anshuman kit, then the equivalent port address is what you have to give out. So here 8000, 800002, 8004, 8006. So port A address for Anshuman kit it is 800. So here you have to give out 800. That means you have to write. So then this you have to write as an steps now. So move AL comma 80 is the command word, step number 1. Move DX comma 8006. If I try to take the control word, it can be 8006 or equivalent address you can give. Then you have to write out DX comma AL. So this is what your step number 1. Initialization of 8255 as output port. And step number 2, move AL comma 88, and you want to move 5 rotations, so move CX comma 1000, 5 rotations, 200 teeths. So this is what the count you load into CX, and this has to be given to the port A, moving it to the forward direction. So the move AL comma 88, so move DX comma port A address, and then out DX comma AL. If you are using standalone mode board, it is suggested to use standalone mode board where you can connect only your trainer kit to the processor. If it is through computer, then that is different story. Right, so this is what the command you give. So move that in forward direction. Now the next step is you have to rotate it to the right. So now here if you try to see, so this is how you, this is not the exact code, so that's what I am trying to show. So then this command word when you give, then you have to give delay. This command word you have to use. Then step number 3, you have to give delay. So delay is move Cx comma the count, not no operation, and then loop here back. So the back loop is here. So if the stepper motor, if it is given of excitation delay of, excitation it is needed for 10 millisecond. So then 10 millisecond thing is what you have to give. So this is what the delay you will write, and then you can use a command, right? This is will be written somewhere else. So then n number of times you are using it. So then you can use a command call, then the delay. So here if you are using standalone mode, the delay address you can give where you are writing. So this is what the delay you have just now seen, and then the count, it has to be calculated like, in the last class we have seen, it should be like C0 plus NCL, okay, NCL minus 12. That means here it requires 4 clock cycles. It is of 3, 3 and 3, and the last, to execute loop instruction, it requires 17 clock cycles. But when it is coming out of the loop, it is taking only 5 clock cycles. So minus 12 is what you have to go ahead. So this is in loop. So here it would be 4 plus 9 plus 17 into n minus 12 is equal to, we need 10 millisecond delay. So it is of, the processor, if it is working with 5 megahertz of 0.2 microsecond, so the number of clock cycles need to be wasted to give 10 millisecond. Okay, 10 millisecond. So you can calculate this, right? So in time domain, if you try to see, it is of 0.2 microsecond by 10 millisecond. So it is of 10 power 3 by 2. So it is of, it's of 0.2, so 10 millisecond is what you are going to see, 10 milli. So then here, this is 10 power 2, so around 5000. So 5000 is the count you can give here, and then you can write a loop. So it is of 5000 is what you can consider. 5000 only, na? Yes. 5, yeah. So it is 10 to, and then it is 0, then 0, 0. 5000 is the loop you have to give, and calculate n. That n will be in decimal, and that you can connect, that you can give it here as a count. Hexadecimal equivalent is what you can give here a count. So then minus 12 is total clock cycles. So this is what the formula we are using here to calculate the total number of count it is required, right? So the next step is what? So you can give delay. So then here rotate the count. So it is of 1000, 1000 and 1000. So then if you can rotate, here if you have one, then if you rotate to left, it will come here and then it will come here. You can use ROR or you can use ROL. Anything is all right. ROR means this bit will go here or this bit will go here. So ROR, and then decrement the count of 1000. And then if it is not 0, again you write the word. Again you give delay. Okay, is it all right? Okay, so this is what? This is, 5 rotations. Up to 5 rotations, the count is how much? 1000. Or if you are using in delay loop CX as your counter there, so then here you can use BX, and then that BX you can decrement. Okay, and then anyhow you are using here jump no 0, so there are no issues. So then here you can use ROR or ROL, anything is alright, because both bits are 1000, then it will be moving in forward direction. And similarly, the next one you have to move it in reverse direction. So reverse direction also for 5 rotations. So rotations, this is what the count you have to load. So move AH, 88, move CX, 1000, and then here write this and to the port A, then give delay and rotate AL to the right, okay, to the right, and decrement CX, right? If it is not 0, right, and then every time you keep on writing the same bit so that it will be moving in right rotations, right? And then you just interrupt. That is what the thing. This is what we have discussed is. So the revolutions per minute you can calculate. This is how. So you can control the stepper motor, or you can interface the stepper motor to 8086 to 8255, and then you can control the number of rotations. So this is how you can do the simple programming, okay, of interfacing 8255 to 8086. Okay, is it all right? Okay, so then now let us try to see the another interfacing, that is analog to digital converter and digital to analog converter. Analog to digital converter interfacing is what we try to see now. So now let us try to see analog to digital converter interfacing is. So any interfacing it is, you have to know the hardware details in clear cut. Okay. So how we have seen here in stepper motor interfacing. So how we started. So once we don't know the hardware of stepper motor, we cannot do anything. So stepper motor cross-sectional details, is what we have seen, how it looks, and then this is treated in terms of, right, these are the four phase motor, the details, and then we have seen the rating. So until unless you know the hardware, how the sequence is, if it is of 1010, this is full step excitation. If it is off step excitation, then you are giving here 1000 only. So we have seen that, and then equivalent diagram, equivalent the winding is what we have seen, right? And that is how we are going ahead. So in interfacing, very important point, without knowing hardware you cannot go ahead or you cannot do anything. So now coming to 8086 interfacing, ADC interfacing, if you try to see any transducer which is connected, or any transducer output is an analog. If you want to use microprocessor to understand what exactly the thing, so if we take an example of sense the room temperature, and then display it. So the temperature transducer output is an analog, but now microprocessor has to understand what is the temperature, and it has to it has to analyze that how much is the temperature. So then here what we do, we will connect the transducer, and we have the transducer, and then the transducer output. So the transducer output is connected to analog to digital and analog to digital converter, and the analog to digital converter is connected to the microprocessor through ports 8255. Right. So this will be the general requirement why we need to interface analog to digital converter, because all sensors which need to be processed for industrial application, the physical quantities, the output of the sensors are analog. It has to be converted into digital. It has to be processed by either microprocessor or microcontroller. So then we need to interface analog to digital converters. And the fastest analog to digital converter here, which we need for 8086 and 8051, is successive approximation time. So then the analog to digital converter input is an analog. We will be using reference voltage to convert it into equivalent digital quantity. Right. So input is 1 and output are based on the resolution. The analog to digital converter, if it is of 3 bit, then the output is 000, 001, 010. So if it is of 0 to 1 volts, it can be given the symbol as 000. If it is 1 volt to 2 volts, 001, 2 volts to 3 volts, 3 volts to 4 volts, and so on. If the reference voltage is of 8 volts, the reference voltage is of 8 volts, and if the input voltage is of 5.5, then the equivalent digital bit is 101. So 5 to 6 volts. It is a 3 bit. But analog to digital converter which is available in the market, it is 0809, which is of 8 bit. Now that is what we have to interface to the microprocessor. So now how it can be done, the internal details of how analog to digital conversion it happens. If you try to see, this is what your analog signal, and if it is sampled, then the number of samples you obtain, that depends upon your sampling frequency. So now if you consider here, this is what your analog, and this will give to sample and hold circuit, and then that will be holding this particular voltage. Okay, this particular voltage up to the next point. This is 3-bit ADC. So now if you take an example, 1 kilohertz sine wave, if it is sampled at 10 kilohertz. 1 kilohertz sine wave, it is sampled at 10 kilohertz, and the time period, if you try to see the number of samples which you get. So the sampling interval is 100 microseconds. So very fast you are getting samples, and it will be having equivalent voltages like this. So this voltage will be held for this particular time, this voltage will be held for this particular time, this voltage will be held for this particular time, and all. So this is 2 kilohertz sampling. If you try to do, sampling interval is 500 microsecond. This is 100 microsecond. And now it is sampled less than the required, sampling required, theorem is not met, then you will get aliasing. And if you have bipolar voltage, then you can convert the bipolar voltage to unipolar voltage by using this particular circuit, so that you can use the same ADCs. Okay. So then, if it is of -5 to +5 volts, then the digital equivalent volt output is this. And the parameters of ADC, this, anyhow it is discussed in your Lika. Then this is what your successive approximation type it is used. And then the pin is ADC0809 is a 8-bit A to D converter. And now the circuit is this. So now this is 0809 internal diagram. And the block diagram, if you try to see here, this is what your 8086 microprocessor. And the 8086 microprocessor bus pins you are going to connect it to 8255. And 8255 is connected to A to D converter, which is of 0809 or 0804. And to read, like, connecting a sensor equivalent means you can use a potentiometer, and the potentiometer here it is connected to 5 volts. So now the input voltage, you can vary the potentiometer, and then you can take a particular DC voltage, and that DC voltage will be converted into digital, and then that digital you can read into microprocessors. So this is what the arrangement. So here you are going to connect your interface 8086 with a sensor kind of thing. So the sensor equivalent taken as a potentiometer equivalent, which is, by varying this potentiometer you will be getting a DC voltage, which is a quantized voltage equivalent is what you can consider, and that you can give it to the input of analog to digital converter, and analog to digital converter is connected to 8086 through 8255. So you should have a clear-cut hardware details, hardware in mind to connect this. So here you have your 8086, and then here you have 8255 to read data bits. So analog to digital converter. So this is what your analog to digital converter, and the input of analog to digital converter, you are giving a particular voltage, and it will be giving digital bits. It will be giving digital bits, and these digital bits you can read through D0 to D7 of 8255 and of any ports. So any port, it can be connected port A or something, so, and this will be connected to internal data bus, and then D0 to D7 of 8255 is connected to D0 to D7 of data bus of 8086. Right, so this is what the hardware details. So what we do in the next class, so once this in mind, to interface A to D converter with 8086, we have to see the clear-cut internal hardware details of A to D converter, how A to D converter look like, and what are the pins are there with A to D converter, and which pin we are going to connect to which pin of 8255, and then we will be writing the algorithm, and then the equivalent algorithm where we are going to write the equivalent code, program code, right? So then this you can verify in your lab by using the existing setup, so that in future you can interface any transducer given to you, and you can process the information using 8086. So in the next class we will be seeing, so this is what the interfacing details we have seen. In the next class we will be seeing the complete code and with equivalent programs, right? So I hope you understood what I am trying to convey, right? So today what we have discussed, if you give a glance, here we interfaced stepper motor to 8086, and we have seen the constructional details of 8086. And when we know the constructions like 4 windings when we are bringing up, and half mode operation is what when we are going, each winding is what when we are exciting once, and how to write control mode and then hardware details is what we have seen, and then the code is what we have seen. So then this you can practice in your lab.